Welcome everybody to lecture number 3, where we're going to talk about the orthogonal coordinate systems. In this lecture, we'll be talking about orthogonal coordinate system, and very shortly we're going to understand what is the meaning of orthogonal, and we'll apply our learning on 3 different coordinate systems, which are Cartesian, cylindrical, and spherical. So in general, why do we need coordinate systems? The main reason for this is to describe objects. These objects can be certain volume, certain surface, like a vector or a point. And when we are dealing in 3D, in 3-dimensional space, we need like a 3D coordinate systems. In your education, in high school and maybe intermediate school and primary school, we talk what is called coordinates when we describe the position of a point on a surface. So this is needed to describe things on a surface, a point, a vector, certain polygon. In 3D, we need the same ability, but for 3D, we need to consider 3D coordinate system. So what is a 3D coordinate system? It is a system that is defined by 3 unit vectors. Let me do this. And those unit vectors, AU1, AU2, AU3, or for shortcuts we write A1, A2, A3, they are called the base vector. For example, the Cartesian coordinate system is very famous, and we have AX, AY, AZ. So those are the base vectors of the Cartesian coordinate system. And if those unit vectors or base vectors are mutually orthogonal or mutually perpendicular to one another, this system is called orthogonal coordinate system. So there can be infinite number of coordinate systems to describe a point or a surface or whatever on 3D. So I don't know what is the count, but I know it is either very large or unlimited. But we care about those 3 major ones. Those are sort of essential ones. And I know that there is others, but they are used for some special figures or special systems. So back to our point of orthogonal coordinate system. We are following the right hand orthogonal curvilinear coordinate system. Curvilinear means some unit vectors are straight vectors, and some of them are curved vectors, as we're going to learn. And curved vectors in general does change its position from one point to the other, as we're going to see shortly as well. So in this right hand orthogonal coordinate system, the 3 unit vectors are perpendicular to one another. So if we have a cross product of AU1 cross AU2, the result would be a unit vector that is perpendicular to 1, perpendicular to 2, and this must be 3, AU3. So those vectors are the unit vectors of a specific coordinate system, and you must keep the order. So it's 1, 2, 3. So if we have AU2 cross AU3, it will give us AU1. AU3 cross AU1 will give you AU2. If we change the order, of course, as any cross product, will have a negative sign on the other side. Because they are orthogonal also, so the dot product between any 2 vectors must be 0, because they are perpendicular. The angle between any 2 of them is 90 degrees, so the dot product is 0. Because they are unit vectors, their magnitude equal 1, and as we discussed in lecture 2, the magnitude of any vector, the magnitude square of any vector equals the dot product of the vector with itself. Because the magnitude is 1, 1 square equal 1. So the dot product of any unit vector with itself equal 1. So those are the three properties of the unit vector of an orthogonal coordinate system, and we're gonna use them all course long, so we must keep them in mind all the time, and of course we'll have some applications on them as we go. So let us start now with the details of the Cartesian coordinate system. So I know that mostly you had came across this in your education before, but we'll have a little bit some different angles and points to emphasize in this part. Okay, so the Cartesian coordinate system, we describe a point in x and y and z as the intersection between three planes. So if a point is at x1, y1, z1, this is the coordinates. The meaning of Cartesian coordinate system is that this point is the intersection between three planes. First plane is x equal x1. So x equal a constant x1 defines a plane, and you need to know this. If I say z equals 0, you know this is the xy plane. Z equal 1 should be a plane parallel to the xy plane and elevated by 1 unit above. So x equal constant also describes a plane. So here on the graph, x equal x1 is this plane. All the points, what does this mean? It means that all the points in this plane does have coordinate of x equal 1. So x equal x1 is this plane. The other plane is y equal y1. So if this is y1, all the points in this plane does have y1 coordinate. And z equal z1, as we just described, are all the points in the plane that does have z equal z1. It's a plane parallel to the xy elevated by z1 units. So the intersection between those three planes is this point, which is the point x1, y1, z1. Also, it's very useful to understand what is the intersection between two planes. So if I told you what is the intersection between plane x equal x1 and y equal y1, we'll find this line. So this line, all the points on this line does have x1 coordinates and y1 coordinates. The only variable would be z. So the intersection between the two planes will be a line. The intersection between the three planes is a point. So this line here is the intersection between x equal x1 and z equal z1. And the line for this line here is the intersection between z equal z1 and y equal y1. So the intersection between three planes is a point. The intersection between any two planes is a line. And as we described, the cross product goes in order x, y, z. So one other important thing to learn is that a vector from origin to a point is called the position vector. So, and it is denoted OB. The starting point is origin, the end point is the point B, and the description for this vector, how would we write it? It's x1 units along x direction plus y1 units along AY plus Z1 units along AZ. So if you are at the origin, you go x1 along the x direction, then you go y1 along y direction, then you go z1 along z direction, you will reach the point B, and the vector, the position vector, would be from origin to the point B. Okay, so a vector A in Cartesian coordinate systems is described as such: AX component in the X direction, AY component in the Y direction, AZ component in the Z direction. AZ, AY, AX, of course, are scalar quantities. AX, AY, AZ are unit vectors. So this is the vector expression in the XYZ coordinate system, or the Cartesian coordinate system. Also, we mentioned that before, the projection of vector A along X equal A dot AX, which will give us A sub X. So this is AX is also known as the projection of the vector A along AX direction, the projection of AY along Y direction, the projection of Z vector along the Z direction, which means the projection means if we have like from a point, so this is the vector. If we want to project this line, this vector along Z, we just go from this point with a line normal to the AZ direction, which is this line, and this will be the projection AZ along the Z direction. As we mentioned before, let me like write this statement here. Okay, we said before the projection, sorry, I'm writing in Arabic. Okay, we said before the projection of vector A along the direction of vector B equal A dot okay. So I'm just like added like a reminder that the projection of vector A along the direction of vector B equal A dot the unit vector along the direction of B, as we discussed in like lecture number 2. Okay, so based on this presentation of vector A in the Cartesian coordinate system, we would go with like the expression for the dot product, like A dot B. We know that the dot product is distributive, so the dot product between A and B is the dot product of, like if we put a bracket around this one, dot product the bracket around this one, we'll find that AX dot AX equal 1. So the first term will give us AX multiplied by BX. This is scalar, this is a scalar. Then AX dot AY equals 0, AX dot AZ equals 0. So the first term when dot product with this side will just give us the first element here. Second term will do the same. Third term will do the same. So let me just adjust the syntax Okay, so the dot product would be the multiplication of the magnitude along x for the two vectors plus the magnitude along y for the two vectors plus the magnitude along z for the two vectors. The cross product for the two vectors, it's the determinant of this matrix. So it's ax, ay, az. Then we write down the components here and like calculate the determinant of this matrix, and this would be the result for the cross product. So I know that all of you knows how to calculate the determinant of a matrix, but it is very important that you practice this so that you do it right in a short time. Okay, it's usually we need to express differential length or differential surface or differential volume in certain coordinate system, and we're gonna like see the application of this when we come to the electrostatic field. So for now, like we need to know like how to express a differential length. Differential length means infinitesimally small length in arbitrary direction on the x, y, z coordinate system or the Cartesian coordinate system. So like for a differential length dl, its expression as a vector is differential distance along ax, differential distance along ay, differential distance along az. If we want to like describe a differential surface, which means a tiny small part of a surface, so assume that you have like sort of like a grid, a paper with grid on it. So each small square on this paper is sort of like a differential surface. So we would like to describe this surface in the Cartesian coordinate system. And note that here we deal with the surface as a vector quantity. So the surface is a little bit different than the area. So if you have like a sheet of paper, this sheet of paper, let us assume it does have 0 thickness. And so this is certain area. When we describe or like when we deal with this kind of like sheet, there is two things that, or like two possibility. Either we deal with the top surface or we deal with the bottom surface. So how would we discriminate? We discriminate by describing the surface with a vector. So the surface as a vector represent like which side of this area that you are talking about. So the magnitude would be the area of the surface, and the direction would be perpendicular to the surface in the outward direction. So like just consider the surface to be your hand. If you are describing the back of your hand, so it would be the area of your hand, and the direction of this surface is going out of the back hand in the normal direction. If you are talking about the inner part of your hand, so it would be the same area but pointing out of the inner hand in the normal direction. For the surface of your desk, if you're talking about the top surface, it is normal to the desk going outward, normal to the surface in the up direction. If you are talking about the bottom of your desk, so it is going normal to the surface in the outward of the surface, which is the down direction. So this is about the meaning of the surface as a vector. So how would we describe this? The idea here is to draw the surface, then define from the drawing the direction of, the area of this part that you draw. So when we are talking about differential or infinitesimal surface, we draw dx, tiny small distance along x direction, dy, tiny small component along the y direction. So this defines a differential surface. The expression for this differential surface is in the AZ direction. Why? Because it's going out of the surface. It will be in the AZ. The area, the magnitude is dx multiplied by dy. If we are talking about the bottom surface of this differential cube, it would be same magnitude dx dy, but the direction is in the negative AZ. So here for this surface, the area is dy multiplied by dz. The direction is dx. Sorry, ax. For this surface, the area is pointing towards the ay. The magnitude or the area of this differential surface is dx dz. So this is the expression of differential surfaces in the Cartesian coordinate system. What is remaining is to describe the differential volume. Differential volume is very small cube that we define, and the volume of this cube is the multiplication of the lengths of its sides, which is dx, dy, dz. The volume is a scalar quantity. So the differential surface is a vector quantity, the differential length is a vector quantity, while the differential volume is a scalar quantity. Okay, let us have like an example here. So the example gives us a vector in Cartesian coordinate system and is asking for the expression of a unit vector b. So it's asking for b, which is a unit vector, in two different cases. Case number one, b is parallel to a and is a unit vector. Case number two, b is normal to a and also it is a unit vector. So any vector in the xyz or Cartesian coordinate system would have this expression. Vector b would have bx in the direction of ax, by in the direction of ay, bz in the direction of az. The magnitude of this vector equal 1 because it's a unit vector, and we need to know the direction. So we need to know its component. So one solution, and this is like a bad solution. Like anyway, I'm just describing because it is mentioned in the book. So because first we need b to be parallel with a, the cross product of the two vectors would equal 0. So if we just apply the cross product, we'll have the three equations, and we have like the fourth equation because it's a unit vector. So solving those four equations together would give us the values for the three unknowns. Those are not fully independent equations. So it's four equations in three variables. So we have like more equations than variables. So they are not all independent. But anyway, just trying to solve this together, we will get the value for bx, by, and bz, and we can get the expression for b. For me, this is like a bad way to solve this problem. The better way to solve it is to use the meaning of b parallel to a. As we mentioned in lecture number 1 about the meaning of two parallel vectors, it means that the unit vectors of the two vectors are the same. This is the meaning for two vectors to be parallel. So b parallel to a means ab is parallel to aa. But ab, because b is a unit vector, ab actually is b. So the solution here that b equal aa, and that's it. So we solve this problem by finding aa. When you find aa, just divide a by its magnitude. The magnitude is 25 plus 4 plus 1 under the square root, which is the square root of 30. So square root of 30 multiplied by a, ax5 minus ay2 plus az. So this is the solution without like going into the hassle of like trying to solve these equations together. Okay, number 2 or number B is that we need a unit vector that is normal to A. So if B is normal to A, it means that their dot product equals 0. So we just need to like calculate the dot product. Okay, let me just see this. And it's giving us like one more information that B is in the XY plane. So in case number 2, B is a unit vector, is normal to A, and is in the XY plane. So we have 3 pieces of information about vector B. So if B is in the XY plane, its expression will be BX in the AX plus BY in the AY. No components in the Z direction. So the cross product, we just like apply this expressions, but BZ equals 0. What we're gonna get is this expression. So we have the relationship here, and now we can just give any value for bx and any value for like we'll find the value for by. Then we make sure that it is a unit vector. So we can put bx equal 1, we can put bx equal 2, we can put whatever value. We will end up with one solution because we are seeking a unit vector. So here for simplicity it assumed like a value of like I think they put like 2 for bx. So it will find that by equal 5. If you put 1, you will find by equal 2.5, whatever it is. Then you divide by the amplitude of bx. You will end up with one unique expression, which is the unit vector for a vector in the xy plane that is normal to vector A. So here, this is the example just to show you like some practice on the Cartesian coordinate systems and their like application. When I say like an assignment, I would like you to go for the book and solve yourself to example like 2.6 and example 2.7. It's a good practice, and this is what I meant by like study. So you need to go and solve examples yourself and learn applying more skills as we go. Now we're going to move to the cylindrical coordinate systems. The cylindrical coordinate system describes a point by the intersection between 3 surfaces. Surface number 1 is a cylinder. Surface number 2 is half plane. Surface number 3 is a plane. Okay, so in cylindrical coordinate system, we have like describes the position of a point by r, phi, and z. So r is the distance from the z-axis. So if the distance from a z-axis is constant, this will draw a surface of a cylinder. So this surface of a cylinder describes the surface where r equal constant. Second coordinate is phi, which is the angle from x-axis. So like the xz plane is phi equal 0. If we just rotate this plane by an angle phi 1, it will describe this area. And we say this is a half plane. Why it is a half plane? Because it's just extending in the outward direction, the direction away from the z-axis. It doesn't go the other side, because the other side is a different angle. That is the meaning of half plane. The third one is similar to the Cartesian coordinate system. Z equal 1 is some plane that is parallel to the xy plane and elevated by z1 units. So the intersection between these three surfaces is the point B in cylindrical coordinate system. Also, it is very useful to understand what is the intersection between any two surfaces. So the intersection between cylinder R equal R1 and half plane phi equal phi 1 is the intersection between this surface and this sort of like shaded surface. The intersection between those two surfaces is this line. It's a surface, it's not a volume. So like we just to consider the surface of this cylinder. So the intersection of this surface of the cylinder and this half plane is this line. Also, the intersection between the cylinder R equal R1 and the plane Z equal Z1 would be this circle here. The preference of the circle, not the whole circle. The area is not included. It's just like a line that does have the shape of the surface, because this cylinder is empty. This is just a surface. So the intersection of surface R equal R1 and surface Z equal Z1 is just the circumference of this circle. The intersection between surface phi equal phi 1 and Z equal Z1 is the intersection between this half plane and this like plane. It would be this vector. So it's going from 0 and extending to infinity in the direction of phi equal phi 1. The intersection of those three things, the circle, the vector, and the other vector, is this point, which is the intersection of the three surfaces, which describes the coordinates of a point in cylindrical coordinate system. And the orthogonality is expressed by AR cross A phi equal AZ in this order. And if you go A phi cross AZ, it will equal AR, AZ cross AR equal A phi. It is very important to note that A phi and AR are of varying direction. At this point here, AR would go from origin to this point, or at this point it would be in a different direction. So AR is a unit vector, but it is not of a constant direction. Its direction changes from one point to the other. Same thing for A phi. A phi is like going away from the z-axis, tangential to this circle. So at this point it does have a direction. At this point here it is going in the AY. At this point here it is going in the minus AX. So A phi also is a varying direction. So the unit vectors A phi and AR change their direction as we go from one point to the other, while their magnitude is constant and equal 1. AZ is the same as Cartesian coordinate system, and it is like of a constant direction. So the Cartesian coordinate system does have this unique property among other orthogonal coordinate systems, which is its unit vectors are of constant magnitude, of course equal 1, and constant direction. So I just added a note that AR and A phi are of varying directions for you to remember that. A vector is described in the cylindrical coordinate system as such: a component in the AR direction, a component in the phi direction, a component in the Z direction. So it is important, very important for you to like know how to like define the direction of AR, the direction of A phi, the direction of AZ for any point in the cylindrical coordinate system. So coming to the same task of describing differential length or surface or volume in cylindrical coordinate system. So dl would equal a component along AR, then a component along A phi. So A phi, like the component along A phi, is a curve. So we must know how to describe the length of a curve. The length of a curve equal R multiplied by the angle, which is d phi, because we move just a small differential distance along A phi, which is corresponding to a differential angle d phi. The z component is similar to the z direction, and because this is a curve, A phi is a curve, this cylindrical coordinate system is a curve linear coordinate system. Curve linear means some unit vectors are like linear, like AR and AZ, and some of them are curves like A phi. For describing like a unit surface, like if we draw a differential, like differential volume, it would look like this. A differential volume is defined by displacement along R, it would give us dr, a displacement along z, which is dz, then a displacement along phi, which is A phi. If we complete like the drawing, it would look like this element, which is similar to like a piece of cheese, like in Tom and Jerry or whatever it is. So it's this shape. This is the unit vector, sorry, the differential volume. If we want to describe the upper surface of this differential volume, as I said, we calculate the distance or the length of each edge and multiply the two edges. This will give us the area, and the direction is going out of the surface in the normal direction. So for this top surface here, the length of this curve is r d phi, the length of this line is dr. So the component here for this like top surface is in the positive z direction. So this is the top surface. If we are describing the bottom, it would go with the same magnitude but in the minus az direction. So the length is r d phi, the length of this curve, and the length of this edge is dr. For this component here, the length is r d phi, the other length is dz, the direction is ar. So ar, first length r d phi, second length or second edge is dz. For this component here, for this surface, we are talking about the surface that is facing, that's going outside. So the A phi is actually the back side of what you see. It's the surface on the other side of the screen, the inner side of the screen. Its edges are dz and dr. Its direction is in the A phi. So it would be like just the edge, or sorry, the surface in this side. And if we are to describe the d volume, it's just the multiplication of the three lengths, or the lengths of the three edges, r d phi, dr, and dz. Frequently, we need to do a conversion from one coordinate system to the other. So here, we're going to just describe the conversion from cylindrical to Cartesian. If we have the vector A in cylindrical coordinate system, this will be its expression. We would like to express it in Cartesian coordinate system. So for a vector described in cylindrical coordinate system, if we want to describe it in Cartesian coordinate system, it would be the same vector but described in a different coordinate system. It's as if like different language. So we're saying thanks in English, it means like teşekkür ederim in Turkish, or shukran in Arabic, or like whatever it is in other language. Or we are measuring the distance, we say, okay, this is like 1 foot distance. It means that 30 point something centimeter, or like if there is like a different units, but it is the same distance. So a vector in cylindrical, when expressed in Cartesian, it would be the same vector but expressed in a different way. So we're saying like it's a translation or conversion. Okay, we need to note that AZ for Cartesian and AZ for cylindrical are the same. So actually what we convert is converting the AR and A phi from cylindrical to Cartesian, which is very similar to what we studied before in school for conversion from polar to Cartesian. Because AZ, which is the third like direction, or the third dimension, is the same. So okay, how to find AX of any vector? Again, remember what we discussed early today. It's the projection of vector A along the x direction. So just multiply A with the dot product of this, with the dot product with this unit vector. So AX is the dot product of any vector with the unit vector AX. A can be in cylindrical, it can be in Cartesian, because it's the same vector. It will always give us AX. So we need to multiply A in cylindrical with dot unit vector AX to get the AX, the projection of vector A along the x direction. AY equal the vector A, whatever the expression of it, and AY. AZ is AZ, the same. So AX would equal AR in the direction of AR dot AX plus A phi in the direction of A phi dot AX plus AZ in the AZ direction along AX. But AX and AZ are orthogonal, so they are perpendicular, and this dot product is 0. We are here using the distributive property of the dot product. So AR, which is a unit vector in that direction, dot AX, which is a unit vector in that direction, the dot product would be magnitude of 1 multiplied by the magnitude of 2 cosine the angle between the two. Magnitude equal 1, magnitude equal 1, cosine angle, which is cosine phi. So the dot product here equal cosine phi. Similarly, the dot product here equal cosine pi over 2 plus phi, which is minus sine phi. Okay, why? Because this is the direction of A phi. This is AX. The angle between them is larger than 90, and it would be negative. So AX would have this expression. In similarity, AY would have this expression. Okay, so now we can convert from cylindrical to Cartesian in a straightforward way. Of course, remember that AZ is the same. Similarly, we can convert from Cartesian to coordinate to cylindrical. So for point X, it's equal R cosine phi, point Y equal R sine phi. So here, remember that, or like just note that we are converting here the coordinates, not a vector. So in this example here, we are converting a vector. In this example or this explanation here, we are converting the coordinates. So we need to calculate R, phi, and Z from X, Y, and Z. So this is converting the position or converting the coordinates. Here we are converting the vector A and express it in a vector A in Cartesian coordinate system. So we are behind the calculation of AX, AY, and AZ. So those are two different things. Here we are converting a vector. Here we are converting just the coordinates. So we need to calculate R, phi, and Z. So let us just apply with this example here. So the cylindrical coordinate of an arbitrary point in the z equals 0 plane. So a point B in the xy plane. Z equals 0 is the xy plane. So the coordinates is r, phi, and 0. We need to find the unit vector that goes from a point z equal h. So a point with z equal x, and it's telling us it is on the z axis. So this point here, we'll call it Q, towards B. So we have a point B, arbitrary point in the xy plane. We have another point Q on the z axis, and you want to calculate the unit vector from Q to B. So the first thing is to write QB, the vector that goes from Q to B. The right way to do it is to move along the directions of the unit vector. So we go from this point to the origin, then from the origin to the point. So this vector here is minus OQ. So it's QO, which is minus OQ, which is minus H in the Z of A Z direction. Minus H in the AZ direction will bring us from Q to origin. Then from origin to point B equal R in the direction of AR. So QB is this vector, and the unit vector along this direction is the vector divided by its magnitude, which is 1 over square root of R squared plus H squared multiplied by QB, which is AR in the R direction, minus AZ in minus H in the Z direction. So this is the solution for this example here. Now we're going to move to the spherical coordinate system. In spherical coordinate system, a point B is represented by three coordinates, R, theta, and phi, in this order. So the point B is presented as the intersection between the three surfaces, R equal R1, which is a sphere, theta equal theta 1, which is a right circular cone with half angle theta, phi equal phi 1, which is a half plane. So phi in spherical coordinate system is the same as phi in cylindrical coordinate system. The coordinate phi, but the meaning is different. But anyway, the intersection between these three surfaces is a point. So R equal R1. R is measured from the origin. So R in spherical coordinate system is measured as the distance from the origin, while in cylindrical coordinate system, R is measured as normal to the z-axis. So there is a difference between R and the two coordinate system. Theta is the angle from z-axis away from z-axis, and theta is changing from 0 along the z-axis to 180 to pi, which is in the negative z direction. It's from 0 to the angle of pi, or angle of 180, which is in the direction of negative z. Phi is the angle with the positive z-axis, which changes from 0 to 360, or from 0 to 2 pi. A vector in spherical coordinate system is expressed as a component in the r direction, a component in theta direction, and a component in phi direction. With this order, and the orthogonality is expressed as AR cross A theta equal A phi, A theta cross A phi equal AR, A phi cross AR equal A theta. It's very important that you know how to draw and express the vectors. So A theta is like tangential to this arc away from z-axis, so it is normal to the arc in this direction. So AR is from origin to the point in the outward direction. A phi is like, if this is the point, so A phi would be like in that direction. In that direction, the tangential to this arc, and this arc is on the intersection between the cone and the sphere. Also here it's very useful to know the intersection between the three surfaces. So the intersection between R equal R1, which is the surface of a sphere, and theta equal theta 1, which is the surface of the cone, is like the peripheral of a circle. The intersection between sphere R equal R1 and phi equal phi 1, which is a half plane, it is like half a circle. So this arc of a circle, or like this half part of the circle, the intersection between theta equal theta 1 and phi equal phi 1 is this line here. This line here, which is in this plane. So the spherical coordinate system is the hardest to draw, but you need to gain this skill, how to visualize and understand the position of a vector or the position of a point in the three coordinate system, how to draw the unit vectors, how to express their directions. Those are very important skills. Okay, so now to the same practice of defining the differential length, the differential surface, and differential volume. So a differential length in spherical coordinate system would be a differential component along direction AR, which is away from the origin, a differential component along theta. Theta is in that direction, and this is a curve. So this curve length is R multiplied by d theta. Then the third one, which is the curve along phi. So this length of the curve here equal R sine theta, which is this length multiplied by d phi. So this is the arc here. The length of this arc equal R sine theta, which is this R sine theta, which is this length, and the curvature would be d phi. So R sine theta d phi. This is the length along the phi direction. And if we are to express a differential surface, so the surface along R, which is this one, it's the part of the sphere going out. So the unit vector is normal to the surface in the outward direction, which equal the length of the two edges multiplied to one another. So this edge is R sine theta, and the other edge is another curve, which is R sine theta d phi. So it's R sine theta d phi multiplied by R d theta, which is R squared sine theta d theta d phi. Okay, in the theta direction, which is this part here that's going down, the length is R sine theta d phi multiplied by dr. So R sine theta d phi multiplied by dr. The third one, which is the a phi direction, which is this surface here, the surface on the other side, similar to this one. The area equal dr multiplied by r d theta, and it is in the phi direction. So we're talking about the hidden side here. So those are the expression of the three differential surfaces with their directions, and the d volume would be the multiplication of the three edges lengths, which is r d theta multiplied by r sine theta d phi multiplied by dr. So r squared sine theta dr d theta d phi. Of course, the directions of theta and phi r are varying direction. So the three unit vectors in spherical coordinate system are of varying direction. Their magnitude is unity because they are unit vectors, but their directions are changing from one point to the other. So converting from Cartesian to like spherical, or from spherical to Cartesian, if we are talking about the coordinates, the relationship between x, y, and z equals this expression, and r theta phi does have this expression. You should be able to like find this relationship and write these expressions from here, from like a sketch like this one. So for x, if this is the point, how would we find the x corresponding to this point? So we go, because I think this would be fine. So if this point is here, let me bring a pen. So if this point is here, this is point B, and I would like to find x component corresponding to this point, what should I do? I bring like a normal to the xy plane, then draw a line. So this one is the x for point B. So this is x for point B. What is this distance? It equals, first we need to find this length. This length is in the xy plane, and it's equal to r sine theta. So this length here is the z component, and it's equal to r cosine theta. So like this rectangular here is in the phi equal phi 1 plane. Okay, so it's in the phi equal phi 1 plane. We have this rectangular, so this is r. The length here, the z component, equal r cosine theta. The length of this projection of the position vector OB on the xy plane equal r sine theta. Then we project this on x, it would be r sine theta cosine phi. So x equal r, let me bring this. So x equal r sine theta. This is the projection of OB on the xy plane, cosine phi, the projection of the projection on x. The y component equal r sine theta, which is the projection of OB on the xy plane, then projected on the y-axis, multiplied by sine theta, and r cosine theta is the z component, which is the projection of OP on the z-axis. And similarly, you can do this. Calculate r, of course, x squared plus y squared plus z squared. We can calculate theta and phi with these expressions. So it's very important to pay attention to the difference between transforming or converting a vector and converting the coordinates. Here we are converting the coordinates. If we are to convert a vector, the easiest way is to do the projection. For example, if we have the vector in spherical coordinate system and you want to express it in Cartesian, so in Cartesian we need to find AX. So AX equals the vector A dot AX. The AY is the projection of any vector on in the y direction, which equals the vector dot AY, so on and so forth. So the idea of converting from the vector is the idea of projecting. So projecting from one coordinate system on the unit vectors of the other coordinate system and work out the geometry. Some people would memorize some conversion matrices. I personally don't like memorization, but it's up to you. Okay, so after this lecture, we'll have like homework number 1, which is due in a week. I will post this on the Google Drive as well as on the IBOSM system, so that when you submit to the IBOSM system. And at the end, this is the learning objectives. This is what we learned from this lecture. After listening or watching this lecture and reading the handout, what you need to do is just review those points and make sure that you understand those points, so that you got the learning intended by this lecture. Thanks for watching the video, and meet you in the discussion session shortly. Goodbye.